The aim of this project was the development of an experimental setup related to mass measurement with load cells. The contents of the project are as given below. Some of the equipments present in the mechanical engineering laboratories create a danger of injury or death. Therefore, there are safety rules for the laboratory which must be strictly followed to minimize risk of danger to individuals by electrical shock, fire, or explosion. Contact with conductors, keeping the hands dry, not wearing metal accessories, and working with right hand only to reduce the risk of current passing through the heart is recommended when working with energized circuits to reduce the risk of electrocution. After accidents with energized circuits, the victim might stop breathing, in which case it should be prioritized to find someone who is certified in occupational safety, which some of the staff in the department office are. The department office should be immediately contacted for help if the victim is unconscious or needs an ambulance. Components such as transistors might get hot enough to cause severe burns. In the event that one of the components on the setup catch fire, turn off the power supply and notify the instructor. If an electronic or electrical instrument catch on fire, avoid using fire extinguishers or water and simply press the emergency disconnect button. Usually small electrical fires extinguish quickly. Components such as electrolytic capacitors carry with them the risk of explosion if polarity is wrongly matched or the voltage rating is exceeded. If such an accident occurs, use the first aid kit, which is located on the wall near the door, and go to the student health service if further help is needed. Mechanical engineering laboratories also have a list of operating procedures, as shown here. Measurement is defined as the act of obtaining quantitative values using a measurement that can be attributed to a quantity with moderate precision. All practical and theoretical features of measurements are the subject of the scientific field of metrology. A solid metrological groundwork allows a country to reliably engage in global commerce and avoid misunderstandings related to measurements. Design and manufacturing of commercial products, the industry, sciences, health and legal regulation all rely on accurate measurements to function properly. Essentially, inability to measure means inability to produce. Due to the vast importance of accurate measurements, there are many layers of metrological institutes that provide services and regulate aspects of measurements in all levels of rigor. All measurements have errors such as measurement errors, systematic measurement errors, random measurement errors, and measurement biases. This causes uncertainty which must be calculated at a reasonable level to assess the reliability of the measurement using both statistical tools related to type A and other methods related to type B errors. After the analysis of the observations, the measurement is finally represented as a value with error bars reported at a statistical level of confidence. Design of experiments is an approach used to identify and assess the interactions and effects of the variables involved in the measurement. The aim is to explain the variation of information and predict its sources under the conditions of experimental design limits. The limits of the experiment, specific conditions, and mathematical analysis is used to obtain the required information spending as little resources and time as possible in experimentation. Experimental designs usually use methods of randomization, blocking, and replication to increase precision and decrease bias. Firstly, randomization is used to reduce systematic and personal biases. In a randomized experiment, experimental materials affected by unknown sources of variation are not systematically selected, but are randomized. Secondly, blocking is used to adjust the variation in experiment to some degree. In a blocked experiment, the experimental unit is divided into groups such that each block is expected to give similar results under relatively similar experimental conditions to a given treatment. This allows the experimental treatments to be compared more precisely, for example, using different skin ointments for rash on two arms of the same person. Thirdly, replication is used to increase precision by repeating the experimental conditions independently. It should not be confused with repeated measurements, which uses the same measurement and experimental subject. Repeated measurements reflects the variation in the measurement process, but replication provides independent results. For instance, if a skin ointment for rash was applied 4 times on an arm of the same person, that would be a repeated measurement. However, using the same ointment on 4 different people under duplicated conditions is replication. Planning an experiment properly requires a wide array of points to be accounted for. These points include definition of the objectives, identification of the sources of variation, determining the measurements to be made, specification of the expected difficulties, planning of the measurements procedure, running a pilot experiment, identification of the model, outlining the analysis, calculation of the number of required observations, and revision at any step when deemed necessary. The definition of the kilogram has a history in the field of metrology. Originally, a kilogram was defined as the mass of the International Kilogram prototype made from platinum-iridium alloy of 39 mm diameter and 39 mm height. The International prototype was the primary standard to calibrate the national standards of platinum-iridium alloys. Due to the contamination accumulation, the reference mass was taken as the mass of the prototype measured after a specified cleaning and washing procedure. The traceability chain of the mass ultimately ended on this measurement. However, on 20th May 2019, the SI unit were redefined using constants of the natural world to ensure the stability of the units. Constants such as Boltzmann constant and the speed of light in vacuum are one of the 7 constants that were used in the redefinition of the system. The SI unit mass kilogram was redefined using relations to Planck's constant, speed of light in a vacuum, and hyperfine transition frequency of cesium. Planck constant is taken as the fixed value 6.626 times 10 to the power of minus 34, which is expressed in the unit kilogram meter square divided by second. Using the definition of meter and second, the value of kilogram is represented as shown here. The main aim of the mass measurement experiment is the following: familiarization with mass measurement and metrology, calibration of load cells, and finally determination of the transducer characteristics of a load cell such as precision, linearity, and threshold value. International Organization of Legal Metrology and International Bureau of Weights and Measures are the organizations that are responsible for defining the standards of mass. The documents and standards shown below are used in mass measurements. After calibration with a proper standard, a mass measurement instrument can then be used to measure the mass of other objects to a degree of calculable uncertainty. There are different types of mass measurement instruments such as strain gauge load cell, capacitive load cell, and those that use force restoration technology. The experimental setup we used uses strain gauge load cell. The working principle of the strain gauge is that it changes its resistance under strain. They are incorporated into a DC Wheatstone bridges to read out the voltage difference, which then gives the resistance change of the strain gauge. The change in resistance is quite low, therefore the reading has to be amplified before registered as data. The strain on the gauge correlates with the mass that is placed on the loading area of the sensor by Hooke's law. The precision of an instrument characterizes its degree of freedom from random errors, but it does not characterize bias. Readings from a precise sample size will have small spread, however, it should not be confused with the term accuracy. An instrument's precision does not imply that it will be accurate. Basic formulas for calculating the uncertainty for a set of measurements for a variable that follows Gaussian distribution are the arithmetic mean, experimental standard deviation, standard uncertainty, and finally the expanded uncertainty at p confidence level. Also, when taking measurements, it is necessary to correct for the zero offset bias, which can be done using the following equation. Measurement instruments have a so-called threshold value, which is defined as the minimum input value that yields an output value if one begins to take measurements gradually increasing from zero. For instance, a car speedometer that has a threshold value of 15 km per hour will not give any readings after it starts from rest until the car reaches 15 km per hour of speed. Measurement instruments are usually designed to give readings linearly proportional to the measurement quantity. A linear transducer input of X and output Y is correlated as given below. Nonlinearity of an instrument is defined as the maximum deviation of the output readings from this line. The mass measurement experimental setup consists of a 1 kg beam-type load cell, a HX711 module load cell voltage amplifier, a BMP180 digital pressure sensor, a DHT22 temperature and humidity sensor, an Arduino Uno, two push buttons, a 16 by 2 LCD screen with an I2C module, a breadboard, a 4.7 thousand ohm resistor, a weight hanger, and computer data acquisition using Python and Arduino programs. The measured voltage difference from the load cell is amplified via HX711 amplifier, and the data is then delivered to the Arduino board, which is interlinked to a computer data acquisition system with a USB cable. Temperature, humidity, and pressure readings are processed similarly through the Arduino program and are displayed on the 16 by 2 LCD screen. The power button on the setup allows for the readings to be stopped once the measurement is initiated. The technical specifications of the main components are given below. For safety and accuracy reasons, the components should not be operated outside of these limits. The setup uses Arduino and Python programs as mentioned before. The list shown below are the additional Python and Arduino libraries that are needed to run the codes. It should be noted that, for Python, these libraries can easily be installed using pip install function in the Anaconda prompt. Temperature and humidity is measured by the DHT22 sensor, and the pressure is measured by BMP180. The temperature-humidity sensor is able to get readings once in 2000 milliseconds, whereas the pressure sensor needs 5000 milliseconds to do it at a reasonable precision. The aforementioned values then are displayed on the 16 by 2 LCD screen and are updated at real time. Mass readings, on the other hand, are written on the Arduino serial monitor. The serial monitor also keeps track of the off and tare buttons. Information on the serial monitor is then transferred to Python using Python's serial library. The Python code is used as the main interface for the mass measurements, and it records approximately 10 measurements per second in ideal conditions. When the code is initiated, the user interface appears, and the interface contains the following features. The user needs to enter here the port connected to the Arduino board. This value can usually be found in the right bottom corner of the Arduino program. The program uses a calibration factor of 1000 and an offset value of 0 by default. If other values are to be used, the user needs to enter here new values. The program has the option to record the measurement session into a file readable by notebook, which is saved in the same location as the Python code. If the user has a set of known mass values and a set of sensor readings from the same measurement session, then inputting that information in the fourth and fifth entries and pressing calculate will yield a linear regression analyzed calibration factors and offset values in the text box in addition to its correlation factor R squared. Pressing the begin button initiates the measurement session and a real-time plot appears. In this plot, the real-time current mass readings can be found just under the title Load Cell Readings. When the Tare button is pressed, the sensor zeroes its offset value such that the current load on the setup will approximately read 0. Secondly, pressing the power button ends the measurement sequence. It is also recommended that the kernel to be restarted before beginning a new measurement session. Calibration is an essential procedure to maintain the measurement integrity of any instrument. The characteristics mentioned before, precision, threshold, and linearity, have to be accounted for in the process of calibration before taking real measurements. It should be noted that there are also effects from loading rates and loading schedules. However, they will be ignored for now for the sake of simplicity. Calibration begins with linearity calibration, which is as follows. First, prepare a load set with known values and equal incremental differences between them. For example, 100 gram, 200 gram, 300 gram, etc. Since the load cell is only certified up to 1 kilogram, loads in the set should not be heavier than that. Secondly, initiate the measurement program and wait for the sensor to stabilize. At the third step, either the readings should be zeroed using the Tare function, or the zero offset value should be noted down. Then, place the lowest weigh-in node gently, record its value, and unload the setup and make a note of the offset value. The average of the zero offset values should be subtracted from the reading to get the corrected reading. This step is repeated until the end of the load set. Finally, enter the recorded loads and readings from the sensor into the program to obtain the calibration factor and offset value calculated through a linear regression model. After these steps, the linearity calibration table should look like this. Linearity calibration is then followed by finding the threshold value. First, prepare a light enough mass set with known values and initiate the measurement program. I've used an A4 paper and cut it into equal halves to get the load set for the lack of a better alternative. A full A4 paper weighs about 3.95 grams, and the smallest piece, 1 over 256th of an A4 paper, weighs about 0.01 gram. Secondly, begin putting loads on the cell beginning from the lightest. If the load caused a meaningful change at the last step, mark that value as the threshold value. If it did not, repeat this step using the next heavier load. The threshold value found through following these steps is not used in calibration exactly. However, it is a useful characteristic of the transducer to know since it marks the minimum value at which the measurements are no longer valid using that instrument. It should be noted that, due to instability of the readings at such small scales, the threshold cannot be determined with confidence for this setup at this level of analysis. The next step is to find the precision characteristics of the instrument. Similar to the threshold value, the information regarding precision is not used to calibrate the instrument. However, the precision of an instrument is a quite useful value to know to quantify the quality of the measurement instrument. The process of determination of the precision is as follows. First, initiate the measurement program and wait until the sensor destabilizes. Second, record the zero offset value before taking the measurement. Then, place the load and record the measurement in the table. Then, unload the setup and record the zero offset value into the table. Repeat this step 10 times. Next, calculate the corrected sensor reading values using equation 6 and record them onto the table. Then, calculate the mean value using equation 2, the standard deviation using equation 3, the standard uncertainty using equation 4, and the expanded uncertainty using equation 5 at the desired level of confidence. Specify the uncertainty as a percentage of the range of reading value and compare it with the value given by the load cell manufacturer. After the calibration steps, the instrument now has little to no linearity errors, its threshold value is known, and the precision information is known, which makes it possible to accurately define the uncertainty of measurements. The mass measurement procedure is as follows. First, prepare the test load and a reference load. Then initiate the program and enable the program to write the data into files. Make a note of the pressure, temperature, and humidity values. Place the reference weight on the balance and wait until the readings to stabilize. Then immediately record the value in the table and repeat this step using the test weight. This method was mainly chosen to eliminate the error coming from the readings arbitrarily drifting and avoid tearing. Repeat this step 10 times for each load. Finally, calculate the average mass difference and record them into the table. Now that the raw data is obtained, the next step is to make corrections for air buoyancy effects and calculate the associated uncertainties, which can be done using the equations shown here.